These are learning notes because I know you have class notes and you have PowerPoints. These are the learning notes. I created these. I'm still developing some more. So, but you have the learning notes for chapter 2 that has all the additional vocabulary and additional examples that you're going to use um, along with what you have in your workbook. So let me go ahead and start. Like I said, chapter 2 is divided in two chunks. The first chunk is all about sets, defining sets, doing operation with sets, um, using Venn diagrams, right, to divide data in categories according to their characteristics, etc. Right. So, if you go to page 25 and 26, you have some vocabulary in there. Okay. Okay. So again, so this is page 25. So I did give you a few vocabularies in here, which by the way, I want you to add, no, that's not it. Mm, I want you to add in this part where it says A looks like subtracted, that is called set difference. A take away B. So that one, this is actually called set difference. So A take away B is called set difference. Relative complement, you write it this way. It's A intersection, that's not like a horseshoe, intersection B, and then a line on top because that is complement. So that's what this is called, relative complement. The thing is that these two, this one and that one, gives you exactly the same set. So the end result of okay. So go ahead and write down or take a picture for you to have because we are going to address these on the PowerPoint. So we are going to add additional stuff to this. So over here, you're going to see on the notes, also on the learning notes, that the natural numbers are also the whole numbers include the natural numbers plus 0. So they can be written down as n for natural numbers and then the subscript 0, or in the class notes I put w for whole numbers. Okay. Um, and then the natural numbers, which is also called the counting numbers, it can be represented just with the n. But in here, I had n sub 1. So we got a set numbers, set of natural numbers, also called counting numbers, and then n, and then the whole numbers, which are called w on the class, on the learning notes, which is just the natural numbers plus 0, because that is exactly what it is, see? Natural number starts on 1, whole number starts on 0. That's the only difference between those two. And then you have integers, rational, irrationals, real, and the complex number. So what you're going to write, and you don't have to draw this one. You can actually, I'm going to show you a nice one on the PowerPoint. But I do want you to keep the sets of the different numbers. The sets of real numbers compose everything that is taught from kindergarten to 6th grade. Okay? We deal with a bigger set later on called the complex numbers. In the complex numbers, when you have imaginary numbers, right? When you have negative numbers inside a square root, that's what we have, those imaginary. And you don't see those until you actually work with quadratic equations later on, and when they're real, and when they give you imaginary solutions, and when they give you real solutions. And those are taught in 8th grade, regular math. So yeah, so there you go. Okay, so you see that there are two branches or two, I call it nested dolls, right? Because one is inside the other. So you have the natural numbers is just counting numbers. Okay, there you go. So again, you have um, the division. So we're going to start with the natural numbers down here. The natural numbers, it is referring to the counting numbers. 1, 2, 3 starts on 1. then those are inside the whole numbers. So it's the natural numbers plus 0. Those are the whole numbers. And then that is what the student will work with all the way to, let me see, I want to say 5th grade. That's 4th grade, 5th grade. And they haven't changed it yet, is where they introduce negatives. Okay, so maybe 5th grade. That's when my daughter saw it. 5th grade. And that's for the negative, the integers. And then again, it contains not only the whole numbers and the natural numbers, but it also contains all the negatives. And then we have all those three are inside what we call the rational numbers. In the rational numbers, it's going to be any number that can be represented as a fraction. That includes, right, fractions that ends, like this one. If you change it to a decimal, it's going to be 0.25, right? Or fractions that repeat, right? When you have, what is it, 1/9? So fraction that repeats, 0.99999. So that also is going to be a rational number, because those repeating fractions we can actually change to a repeating decimal, we can also change back into a fraction. And we actually see that in chapter 6, I think. And then also you need to be aware that anything that represents a natural number or a whole number or an integer can also be written down as a rational, just by writing it over 1, right? So if you have 5, 5 can be written down over 1, and now it's a fraction, right? Or you can have -5 over 1, and it's also a fraction, okay? Or 0 over 1, and it's also a fraction, right? So any of that. And then one that students dismiss a lot is the square root of 9, or any square root of a perfect number, okay? So remember the perfect squares. What do we have? 1 square is 1, 2 square is 4, 3 square is 9, right? 4 square is 16. So 1, 4, 9, 16, those are perfect squares. And the square root of any of those perfect square is going to be a natural number. And those obviously are not only are rationals, they're integers, they're whole numbers, and they're natural numbers. So a single number can be in multiple categories or in multiple sets, because this is what they are, in multiple sets at the same time. Now, what is not in the set of rationals? The irrationals. Those are decimals that do not end, do not terminate, and they do not have a pattern. They keep going on forever, okay, with a different pattern, just like pi. Pi, we approximate pi to 3.14, but that is not pi, right? Pi continues going on forever. And also, if you recall from your college algebra classes, maybe, when you did exponential functions, right? You use the e as the base. We rounded to 2.70 something. So again, but it's an irrational number. And as you see, there's also in there square root of 2. Any square root of a non-perfect square is going to be also irrational. Okay? So that number, that radicand, that number inside the radical, it cannot be a perfect square. Okay? And they will be irrational. So make sure you write this down. And the group of both of them is what we call the real numbers. That's what I'm saying, that this is the essence of kindergarten to 6th grade. We go over all of these. Okay, so these are definitions that you already have. You have these definitions right here. But again, if you need some more information, you can always go ahead and look at the learning notes. Okay, I did have a little quick practice because students tend to make a mistake of when they have to classify, they only classify it in one specific one when they're actually more than one set. As a number can be more than one set. Now, there is an activity about sets and classifying items in a set in your workbook, which is on page 27. And the counterpart that you will have to like cut out and classify and stuff like that, it is on page 147. So you need to take those items in page 147, cut them out, and classify them according to their properties or whatever you can see into the three sets that you have on page 27. Okay. And then who created all this information? Well, Cantor is the first mathematician to refer to sets as a group of collection of, it can be anything, items, whatever you're collecting, and define them with a capital letter. See here, he called it M. And then those objects that are inside that set M are called elements, right? So he's the one that defined what we know about elements, what we know about sets, how we define sets, and then they have to be well defined, okay? So this right here, you should be able to take a picture because I want you to write it down. You need to be able to know that sets are always named with a capital letter. Okay, that's why you saw that the set of whole numbers, we did W, the set of rationals, we did Q, the set of natural numbers, we did N, the set of real numbers, we did R, the set of irrationals, we did I, right? So that's why we use those capital letters because they're sets of numbers in this case. And those numbers have a specific property, characteristics. So in this case, right, I have set P as a set of polygons, okay? So, and as you see, like I said in here, the elements, they don't have to be written down in any specific order. What it is important is that you don't repeat. So, for example, let's say that we had another rectangle. We only have one. This is a square. So let's say we had another rectangle. We don't have to repeat rectangle twice, okay? Because it is already there. So we don't repeat the same elements. We only write it once. And the order is not important. And then we're going to use this weird E, which basically the way to write it out is write a lowercase c and then put a little line in the middle. That's how you write this symbol that represents elements that belongs to a set and elements that do not belong to a set. And you do, as a matter of fact, have this definition in your workbook on the bottom of page 25. So you do have these. So if you want to add it, that's fine. But if not, make sure. Now, what I did tell my lecture students actually today, I told them to go ahead and the definition of sets, which is the first one that you have on the first page on 25, is to add this information that you use capital letters to represent sets, that each element, each object is called an element or a member, right? And that the order is not important and that we do not repeat elements when you're writing it out. Okay? So, okay. Now, very similar to what you have on page 147, right? And page 147, you have like some geometric figures, you have some circles with different colors, and then you have some bears. Actually, those are bears. My students said that they look like panda bears, but they're bears, okay? So, and even though those bears are made of circle, most of their body is made of the face is made of circle. I do not consider them a circle per se, okay? Just as important because you're going to try to classify these in different parts, right? According to their appearance. And then the reason I wrote down the name is because originally the workbook was only going to be printed black and white. That's why I had to literally write the name of the color in there. So, so let me actually, where did it go? There we go. Why is it not here? Okay. Ah, Jesus, why you make it so hard? Okay, it can't. Give me 1 second, guys. People think that it's easier. No. Okay. Okay. Go to your course. And let me go to course resources. And then let me go on course resources to class activities. And there it is. This one. Okay. Okay. So according to the, let's see if I can move this over here. I don't know right now. Are you guys, what are you guys seeing right now? Are you seeing the PowerPoint or are you seeing something else? I don't know what you guys are seeing. Let me see. I think this one. Is that what you're seeing? The workbook? Let me see. Okay, thank you. Okay, so as you see, there's different ways that you can classify this, but in general, the students, right, you do want them to struggle a little bit, right? So, and then to talk with each other, to discuss it. So they will see, you may ask them, what do you see a lot of, right? If you want to direct their attention. And they're going to see, oh, we have a lot of circles and bears, or whatever you want to call it, right? And it says, perfect. What else do you see a lot of? And if they actually are colored, like if they, I tried to color there, I don't know if you can see it, but if they're actually colored, they will see that they have a lot of blues, right? So that means that we can divide these items by these categories, right? One category is everything that is blue. Another category is everything that are bears. And another category is everything that has circles, okay? Now you see that there are a few things that have both of them, and there's a few, and one thing that doesn't have any of them. So we have a blue circle. So the blue circle is going to go with the area where the sets overlap, because this one is on both sets, right? And over here we have a blue bear. So this one also overlaps between the bears and the blue. But since I tell you that I do not consider the bears a circle because it doesn't have this exact shape, right? Only. So that means we are not going to put it here, because in the middle, it only going to go whatever you have in common with all three of them. So this is why you are going to see, I don't know if this one is all defined that I did. Oh yeah, I did do it. Okay, that's what you're going to see, that we can define these areas. See, there's 8 areas, okay? Because as you see over here, the flower is neither a circle or a bear or is blue. But nevertheless, it's part of this group. So as you see, the rectangle includes all of the items in the set, okay? And then you're subdividing those sets, those items into particular characteristics, and then you're grouping them together, okay? So I suggest to be able to, for you guys to do like page 28 and page 29 and page 30 and page 31, you are going to have to know this vocabulary, the vocabulary of only A, only B, or right? So you want to be able, in this case, because you have 3 Venn diagrams. On the homework, I only put 2 Venn diagrams, which is much easier. You only have 4 parts. But when you have 3 parts, because I think on the test I did put 3. So on the test, for example, you have something very similar to this. You have 3 circles or 3 sets, and they overlap. They're all overlapping. So you see that it is dividing the rectangle, which is what we're going to call a Venn diagram, and is the universe, is actually, it actually has 8 parts. 1, 2, 3, 4, 5, 6, 7, and then 8 is outside the circles, the sets, but inside the Venn diagram. Rectangle along with these is called the universe. So, and we label it with a capital U, universe. Okay. So take a picture, or this is part of the answer key for the workbook activities that you have under class activities. So it's up to you, but it will be much easier if you just have it handy and write it down so you can see it. So 1 is where it's only a bear and is neither a circle or is blue. So that's what it says, only A. But if you have a blue bear, it will be just right in the middle because, sorry, here. A blue bear will be just right here and not here, because in this part, it will be the one that actually satisfies all 3 of them. Okay, so this one only satisfies these 2. This one only satisfies these 2. This one only satisfies those 2. This one satisfies all 3 conditions. Okay. And this one doesn't satisfy any of these conditions, any of these characteristics. Area 1 is only for bears, right? Not circles, not blue. Area B, area 3, which is only B, that means it's only a circle, but it's neither a bear or it's a blue. Area 7 is only blue, but isn't either a bear or it's a circle. And then we're going to go back to area 2. Area 2 is only a bear and circle, but it's not blue. So that's why we don't write it on area 5, because area 5 will be all 3 of them. Okay, all 3 characteristics. I hope that makes sense. So that's what it says, only for A and C, only for A and B, only for B and C. See? So area 5, it has to be all 3 of them, A, B, and C. And then we have area 8 is not in A, B, or C, right? So it's not in either one of those 3, but it's part of the universe, okay? And this is a fun characteristics. And yes, you do need to introduce not maybe that much information for them at the beginning, but you do need to introduce this early on, because you are classifying. You're going to, in kindergarten, we do touch base with, for example, polygons, right? So we say, oh, this figure, what shape does it have? How many sides does it have? Oh, it has 3 sides, 3 pointy corners, right? So 3 angles. So they need to be able to recognize the shape and the characteristics of that shape. So you do this early on. So they may not know that this is called a Venn diagram. They may not know that these are characteristics, but you want to be able to, to do certain activities. I was showing my students, I'm not in the classroom that I teach where I have all my manipulatives, but I was showing my students, I have a bag of weird shaped, different color buttons, and they're big. And sometimes I use them like to sit arrangement students around, right? But you can use that. So I have some shapes like a head of the bear, just like this one that you have here. And I have one that actually is like a little gummy bear shape, and it's a button. And they have different colors, right? So they can actually, you can do certain activities like that. So you don't have to use buttons. You cannot have this. You can be creative as much as you want, right? So this one, I just came up with these figures, okay? But you can do whatever you want. You don't have to use these figures, right? So yeah, so this is the activity. And then for this one specific, which is on page 28 and 29. So you have something very similar to this on your homework. And you're also going to have something very similar with this for your test. Now, the thing with this problem is that I first try to like give you a little bit at a time and not all completely together. So in this one, I give you a Venn diagram already set up with different numbers, and you needed to answer the questions according to the statements. Oh, in this case, questions. On the test, you may have to build the diagram given the statement. Like I will give you this part, and then obviously with numbers, and then you will have to build it and shade it in. Just like you have these right here, you're gonna have to shade it in. I may give you the shaded in, and you need to write the set notation and the word form. Now, what do I mean by the word form? You see how it says in here, how many students like baseball or swimming? We are going to see that that word or is part of a union. Okay, that's another part of the set notation. In the words and, let me see right here, and is part of the intersection. And the word do not like or do not do swimming is part of the set subtraction, like the one that you take away, or the complement. So those are two. So those words, those adverbs, and those conjunctions mean something. Okay. So they mean something in the set notation. So I may give you, please tell me, like I may give you the literal sentence, and then you need to tell me identify, just like this one. But then I also may ask you the other way around. I may give you this one, and then just like this, and then you need to tell me the set notation and what does that represent. Okay, so it's like a mixture of these two activities, what you have in your homework and what you have in your test. Okay. So let me go back to the PowerPoint. So I just want you to, when I'm talking about this time, this period of time and this vocabulary, but then again, you may want to write it down because you don't have it on your workbook. Set needs to be well defined, no ambiguity. So what does that mean? That means that you do not use opinions, and they need to, like, if you ask everybody the same question, the answer is the same answer, right? So it is not going to be a different answer according to the opinion of the person. Okay, so right, I give you here a few examples. So for example, the collection of US presidents. And I'm not a history teacher. My worst subject always was history. So I'm not a memorization type of person. So, and I never find politics exciting either. So, but if you Google, right, if you Google the US presidents, you can tell me uh, all the presidents that we have had in the United States, right? And everybody should have the same one. There's no ambiguity in there. So that means that number one is well defined. But number two, the collection of the 5 worst US presidents. So what's going to happen? Do you think everybody's going to have the same answer? No, right? No. Why? Because it is an opinion. So it's whatever the person thinks is an opinion. So that is not a well defined. And then you want to put, if you're writing these examples, you want to put why, because then you're staring at home and it says, why is not a well defined? Because it's an opinion. Opinions are not they're not a set, period. So they're not even considered a set. And then look at 3, the collection of even natural numbers greater than 100. So do you think that is well defined? Yes, right? It is well defined. And not only that, you could even write it if you wanted to, right? So you can write, okay. So if I were to write this, if I ask you, because this is just a statement, right? The collection of even natural numbers greater than 100. So that is well defined, right? And we can say, let's say that we call this set C. And then we have the set C is equal to, you can barely, I don't know why this is so thin. Okay. Set C is equal to what? Is 100 included in there or no? 100 is not included, right? Very good. Because it says greater than 100. If it says greater than or equal, then yes. So, and since we're talking about even natural numbers, in which number am I going to start this? Since we know that 100 is not included. 102, very good. So we're going to do 102, okay? And then 104, 100, right? Because it's even natural numbers, right? And then it will continue, right? You will have to put a dot, 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 the ellipsis at the end, because it's going to continue in that manner, okay? So when we talk about cardinality of a set, we're talking about how many elements that do not repeat are in that set, okay? So in this case, we have the set A that contains the elements 1, 2, 3, A, B, C. So that has 6 elements. So we're going to say, and this is how we write it, that lowercase n implies number of elements. And a number of element of whom? That's what is inside the parentheses. That is labeled a set. Number of elements of set A. So the number of elements of set A will be 6 in this case, okay? And then sets, the only sets that you can actually tell me the cardinality, it's sets that are finite, sets that ends, right? So, because if I tell you, tell me all the numbers in the natural numbers, or like that previous problem, right? That talked about what? The collection of even natural, that keep going on forever. So that's an infinite set. I cannot write all the elements, right? There's no cardinality for infinite sets. But can I write the number of presidents of the United States? Yeah, I can write a set with all 47 of them. So, yes, so we are going to see here 3 examples again, and you need to classify them as infinite or finite. And if it's finite, then you're going to give me the cardinality of the set. So set W is the sets of the week. So that means what? That means that we can name them, right? So Sunday or Monday, whichever one you want to start with, right? Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. I always end my week on Monday, but people ended it and started on Sunday, which is, I think, is what it's supposed to be. But anyways, so it's a finite, and we only have what? 7 days in the week. So we're gonna say that the number of elements of W is 7. But look at the next one. N is the set of the natural numbers. We can't name them. We're just gonna say it's infinite because it's going to keep going on. So this one has no cardinality. You can only say that it's infinite. And then set L, right, is the set of lowercase letters of the English alphabet. And this is important because in Spanish we have extra letters, right? I don't know, I know the real Spanish Academy has changed some letters, but when I went to school, we have CH, we had double L, so we had an additional 2 letters, 3 letters, because there's also ñ, is the N with a tilde. So we have 3 additional letters that the American alphabet did not have. So again, so yeah, so I don't know if they took the CH off or not. And then I don't know if they still kept the double L, but yeah, so you want to be able to specify that is the English alphabet, right? So make sure that they have it all. So now that you have specified that lowercase letter, so if you ask them like, and here I'm asking you for cardinality, but if I asking you to write them out, like to list them out, then again, it is important if you say if it's lowercase or uppercase, because then they can write down the uppercase and then it will be incorrect, okay? So this is finite, and in the English language, we have 26 lowercase letters, right? So that's why you see that it has to be so well defined, because it matters, okay? It matters. And like I was telling you, oh, translate, yes. You are going to have to translate between word form, roster or listing form, and set builder notation. And yes, the set builder notation have different parts, okay? And I don't think I put it in your notes. No, it's not in these notes. So yeah, so you may want to, again, take a picture or write it down, because you are going to have to translate. So I say, oh, like that previous one about the lowercase letters of the English alphabet. So you're going to have to write it out. So because I gave you the statement, the word form, and you need to, like I'm asking you to do the listing form, right? So again, so you may have to be able to translate from one version to another. And then also going from set builder to roster or set builder to word form, right? So you do need to recognize how to write these. In these 3, I use the same statement. I is the set of the integers that lies between -1 and 5. Since I don't have between or including, right? That means we're not going to include -1 and we're not going to include 5, right? So we're only going to include the numbers in between -1 and 5, which is 0, 1, 2, 3, and 4, right? And then how do we write it in the set builder notation? Again, so you're going to start with the set name equal, and then you're going to do the braces, and then you're going to say the set of all x's, and that line means such that. So that line does have a meaning, such that x is an integer, comma. You can also put and. So in this case, I just put comma, and x is greater than -1 and less than 5. So basically, when you have this type of inequality, you want to read from the middle. You want to read from the variable. So kind of like cover the less than 5 and then read here. X is greater than -1. Well, -1 is less than x. That means that x is bigger, right? And then x is less than 5. That means x is smaller than 5. N is an integer, right? So there you go. One-to-one correspondence, okay? So this is important since early on, because you want students to learn how to count and how to quantify, is it quantify the word? Acknowledge what they have counted and what they have not counted, okay? So, or how many of those are trucks, or how many of those are dolls, right? So in this case, when we're doing like the formal definition of one-to-one correspondence, right? We can get each element of one set, in this case set A, see it's right here, and we can match it with one element of the second set. Only once. So for example, if 1 goes to G, then you don't have G available anymore, right? That means that 2 can go to R or L. That's why you see these 2 options right here. And if G goes to 1 and R goes to 2, then whatever is left is L. So see, there's a one-to-one correspondence between the elements of B and the elements of A. And once you find all the possible combinations, arrangements, you have the total one-to-one possible one-to-one correspondence. And like I said, we can do a table display or we can do a tree diagram display. Either one of those two. And again, this is just explaining what I just told you. So that's what it's explaining in there. Okay, so one-to-one correspondence. And again, why one-to-one correspondence? What I was just telling you. It is crucial for my concept that adults frequently take for granted. The skills entails counting each item in the exactly once, ensuring each object is touched only once. For instance, a child who touches each toy car in a sequence and says the corresponding number out loud, such as 1, 2, 3, 4, is demonstrating one-to-one correspondence. So as you see, what you learn here not necessarily is, oh, am I going to teach this in kindergarten? Yes. You're not going to tell them, oh, you're doing one-to-one correspondence, but you are doing it. Not telling them, but you're doing it. Okay? So you are practicing it. Okay? And then when children lack this grasp of this concept, they often find basic math challenging. So therefore, right, we want to be able to don't waste any opportunity since kindergarten or even before that, if you guys doing pre-K, right, to be able to emphasize one-to-one correspondence in the classroom. Okay. So activities that develop one-to-one correspondence. And you as a mom, as a new mom, you can do this with your kids too, okay? Mom or dad, I'm sorry, I didn't want to discriminate, right? So some easy strategies. What can you tell your kid? Count together, count your snacks, give them some goldfish and count them. Do you have more or less than me, right? So how many do you have? Can you count them for me? So again, same thing with a child, toys. If they're fighting with their sisters or brothers or whatever, who has more toys, right? Or you want to have even number of toys. Again, sharing is caring, right? Like Care Bears. But so again, you want to be able to give them all ample opportunities to practice at home as well. Point and count, right? So encourage your child to count. So if they're in the car, just tell them to count the trees. How many trees can they count out loud? Move and count. So have your kid actually move one pile and ask them, so how do you know if you already counted these? Oh, because in this pile, I already put the ones that I counted, right? In this pile, I haven't finished counting yet, right? And give them pennies and have them just group them together, right? So again, you can do so many different activities, easy things, right? To keep them entertained and get that math mentality going on, okay? Now, the fundamental counting principle tells you the different ways that an event can occur according to different sets. So let's say that you are going to a conference and over the weekend in Atlanta, and you're taking 3 shirts and 2 pants. And let's assume that they all match, right? So you can say, how many outfits can you have, right? Shirts, and then you have pants, right? And let's call the pants 1 and 2, because you have 2 pants. And then you need to find all the possible combinations, right? Or outfits that you want to create. So you can wear shirt A with pant 1, or you can wear shirt A with pants 2, right? Or you can wear what? Or you can wear shirt B with pants 1, or you can share shirt B with pants 2, or you can share C with 1, right? Thank you, Karen. And then C with 2. So how many total outfits do you have? So how many total outfits? We got 6, okay? But this is what's easy because I only have 3 shirts and 2 pants. What if I make it bigger, right? What if I make it, bigger? And instead of having just 3 shirts and 2 pants, I have 3 shirts, 4 pants, I don't know, 6 pair of shoes, 3 jackets. It's gonna get gigantic, all the possible combinations to do it like this, right? To do it with a matching or to do it with a table, right? So what is a shortcut? So the shortcut is what the counting principle says. You are going to have the set S, let me write here the number of elements, has 3 elements, right? And the set P has 2 elements. So the counting principle says multiply the number of elements in set S and multiply the number of elements in set P. So it says to do this, multiply N of S times N of P. And that's going to give you the total number, which it does, right? Because this is 3 times 2, which is 6, okay? So here I included a video of the Khan Academy because they had like pots and flowers, like something appropriate for elementary grade level to explain what counting principle is, right? But look at this one. So this one we have burgers, we got 3 types, we got sides, we got 2 types, and then we got sodas, drinks, we got 2 types. So this is a bigger options. I'm just adding one more option, right? I'm adding there the drinks. So once again, we can use the tree diagram or we can use the table. In the tree diagram, right, it would look something like this. So I'm going to start with the burgers. You'll have the beef, chicken, or fish. Sounds like McDonald's, right? When they have the Chick-fil-A, what is it? Fish, the sandwich. I haven't eaten that in a long time. Anyway, so we have that. And then you can select between fries and salad, definitely not McDonald's, right? Fries and salad, fries and salad, fries and salad. And then from there, right, so you can have beef, fries, and cola, or beef, fries, and juice. That's 2, right? Or you can have beef, salad, and cola, and beef, salad, and juice. That's total of 4. And if we repeat the same thing with the other chicken sandwich, that's another 4. And if we repeat the same thing with the fish sandwich, that's another 4. So we have a total of 12 different possible arrangements, right, for this one. So, but again, we can use the counting principle in that case and do a 3 times 2 times 2, and that is your 12, right? So that's the shortcut for those 12 arrangements using the counting principle. Now, again, you do not have this definition in your vocabulary, I would say vocabulary pages. So if you want to go ahead and add it up there on page 26, disjoint sets. What are disjoint sets? And this is important because I'm going to refer to this again when we get to chapter 3 and we define addition. Addition is defined as the union of 2 disjoint sets, right? Sets that do not have anything in common. That's what disjoint means, okay? Hold on. I'm sorry, in this classroom, if you don't move for 10 minutes, it just turn off the lights and I have to move again. Okay, so yeah, so we see right here, this is a Venn diagram. That's what we call these. A Venn diagram that has the universe, the universe is the whole rectangle. And it has two sets, set A that contains 1, 2, 3, 4, and set B that contains 5, 6, 7, 8. We are going to set that these two sets, A and B, are disjoint because they do not share any common element. See, they're not overlapping. If they're overlapping, they have something in common. If they are not overlapping, they do not have anything in common. Okay? We also, like I said, that rectangle, we call it the universal set. So your classroom is your universe. Everybody in your classroom. Do you want to classify them in different little groups? You can classify them in little groups. Those are going to be your subsets. They're going to be the sets that you have inside that universal set. Okay, but everything in the classroom, including you, is part of this universal set. Okay, it's still a set, and we label it with capital U. Okay. Now, again, besides the universal set, you see that we use, in this case, I use circles, but I have in the PowerPoint that we define the different number sets, right? I use ovals and rectangles. So again, it is not just circles. It's most commonly used, okay? Most commonly used is circles and ovals, but not, but it can be any geometric shape, okay? And that is called a Venn diagram. And Venn diagrams are very useful for illustrating relationship between different sets with a universal set, okay? So for example, right, just like you guys did with the bears and the blues and the circles, right? So there'll be some things that have in common, and that goes in between. So you see, when you only have two sets, not three, like in the example that I gave you, that you have in your workbook, you have divide the universal set into four parts. See, only D, only E, share part with D and E, and not in D or E, right? So those are the only four parts in this case for this overlapping sets. So we see here that D includes 1, 2, 3, that E includes 2, 3, 4, 5, and then the universal set includes 1, 2, 3, 4, 5, 6. So we can say that D is a subset of the universal set, and E is also a subset of the universal set. Why are they subsets? Because there is a bigger set that contains them, right? Remember, like the real numbers include all the rationals and all the irrationals. And all the rationals include the integers, the whole numbers, and the natural numbers. So again, they're little pieces of the big one. So those are what they call subsets. And we have different type of subsets. We have what we call the regular subsets, right? And we use that sideway U with an underscore because, right, the set itself, so the universal set itself can be a subset of itself. So you can say, okay, so how many subsets can I have? So you can say, so any of these numbers by themselves can be a subset of the universe because they are individual and they're part of the big one. Okay, so that's what we said in here, that D is a subset of U, that E is also a subset of U. Okay, and that's what that symbol denotes, subset. And we can say that set A is a subset of B if A is inside B. See? A is inside B in this case. So A contains Y and X, or X and Y, and B contains X and Y and Z. So don't lose focus on that. Since all the elements of A are inside the big circle B, so they're also part of B, okay? So yes, we can say that A is a subset of B. Now, can we say that B is a subset of A? Not in this case, right? Because B has an extra element that A does not have, okay? So it's important that you're careful when you're writing those subsets. And you do have a problem that you have to do like exactly the same thing that I'm doing right here in this problem. You're going to have to do it on your homework, and you're going to have to do it on the test. One single problem like this one. Okay, so it says consider the following. Let set T be that set that has those three elements, 1, 2, and 3. So we are going to label all the possible subsets that can arise from these three elements. The empty set you are going to see is always going to be a subset of any set. So the empty set is always, see right here, the empty set is always going to be a subset of any set. Okay, so we're going to have the empty set, and then we have 1 by itself, 2 by itself, 3 by itself, and then we have the pairs 1 and 2, 1 and 3, 2 and 3, and then we're going to have the set itself. So you see the set T, which is 1, 2, 3, is also going to be a subset of itself. That's why we have this little underscore, which means that you can include the original set, okay, the set itself. That's why we put that equal. It's just like saying less than or equal or greater than or equal, right? That includes whatever is equal to. So same story, okay? So not only you're going to do each individual element or pairs or triples, depending on how many elements you have, right? You're also going to include the empty set, and you're going to include the set itself. So if we count with 3 elements, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 subsets when you have 3 elements, okay? So again, this is the definition of subset, and I did put subset defined in your vocabulary on page 25, so you're welcome to add to that or just leave it as is. And then you have, I added one more. Look at this. P now has 4 elements, not 3. So I'm going to find all the possible combinations, all the possible subsets with 4 elements. So I'm going to have the empty set, because again, the empty set goes with everything. And then I'm going to have each individual element by itself, A by itself, B by itself, C by itself, D by itself. And then I'm going to start the pairing. So I'm going to do a B, a C, a D, BC, BD, and CD, right? Those are all the pairs. And now I'm going to do the trios. ABD, ABC, ACD, BCD, and then the set itself, ABCD. So if you count with 4 elements, we have 16 subsets. So the whole activity, right, the activity that you have on your homework, it says that you have to come up with a formula. Now, on the homework and on the test, I ask you to do 2 things. I ask you to write all the subsets, just like we did here. And I also ask you to write, like I give you another problem, then I tell, what if you have 15 elements, right? I don't want you to write all 15 elements. I want you to tell me how many subsets you have. And for that, you are going to use a formula, okay? And the formula, we are going to see that is derived, we can derive it in a minute, okay? Now, what is because I told you there were 2 types of subsets. So subset is anything that includes from the empty set to the set itself and any combination, and I should say not any, all possible combinations of the elements inside. Proper subset, on the other hand, is going to be exactly the same thing as a subset, except the subset itself. Okay, so we cannot include the universal set. You can include everything else except for the universal set. So for this same problem, right, that we had XYZ, I can say that A is a proper subset of B. Why? And you see there's no more underscore because we're not including the set itself. There's no underscore because B, the bigger set, needs to have at least one more element than the subset, than the proper subset. That's why we cannot include the set itself, okay? So again, to be a proper subset, it will have, the bigger set has to have at least one more element in the set that is not in the proper subset, okay? See, that's what I just said, at least one more element. So let's go back to set T that had 1, 2, 3. So that means that the proper subset of set T is just going to be the empty set, 1 by itself, 2 by itself, 3 by itself, 1, 2, 1, 3, and 2, 3. I cannot include the 1, 2, 3 because that will be, there will not be any additional elements in the set, right? So all of these, at least I have one that is not inside these sets. So that's why all of these are proper subsets, okay? And that's what I say, I cannot include 1, 2, 3 because it would not have any additional, right, in there. So to derive, and then this is just improper subset is such a good definition that is not proper. Improper subset is just referring to the set itself, right? The universal set. That's what they call it improper, but it's okay. You don't have to remember the improper. Let's see here. Let me move on. Now, can we find the pattern? This is the important part because again, you're not going to do if the elements are 15 elements, you're not going to do all the subsets. That's horrible. So let's find a formula. So we're going to refer to n as the number of elements in the set. Okay. So if we have only one element, then we're going to have only two subsets, the empty set and the set itself. And then we're only going to have one proper subset, the empty set. If you have two elements, then we're going to have the empty set, each individual by itself, and then the combo, right? And that's 4 subsets. But in the proper subset, you're going to have only 3 because, again, we cannot use that one. We cannot use the set itself. On set C, we got 3. This is just like the set T that we saw before, right? That we saw that we had 8 subsets, right? By itself, the empty set, by itself, the pairs, and then the trio. And then the proper subset will be 1 less because it is not including the full set, the universal set, right? We even did 4. We even did the 16 one. So proper subset will be 15 because, again, we're not including that last one, right? That includes the universal set. So pay attention and look what happened to the number of subsets according to the number of elements in the set. We have 1 element and we got 2 subsets. We got 2 elements and we had 4 subsets. We had 3 elements and we got 8 subsets. We got 4 elements and we got 16. So first, what do you notice on the number of subsets as we increase the number of elements by 1? So Terrence says you're multiplying by 2 the previous term, right? So yeah, so it is doubling, right? So from 2 went to 4, it doubled. From 4 went to 8, it doubled. From 8 went to 16, it doubled, right? Correct. It is double. Now, can I represent 4 in terms of 2? Right? Can I represent 4 in terms of 2? Yeah, it will be what? 2 squared. Can I represent 8 in terms of 2? 8 in terms of 2. It will be 2 cubed. or 2 to the third power. Can we represent 16 in terms of 2? That will be 2 times 2 times 2 times 2, right? So it will be 2 to the fourth power. You see what I'm saying? 2 to the fourth power, 2 to the third power, 2 to the second power, 2 to the first power. So we are using the number of elements as our exponent of the base 2, right? So if I tell you that we have 15 elements, that will be 2 to the power of 15. You're probably going to have to use a calculator, right? Not do it by hand because it's going to take forever. But 2 to the power of 15, sorry. Which will be what? Let me see. It will be 32,768, right? So we don't want you to do 32,768 subsets, right? So, but if 2 to the power of 15 is 32,768, how many proper subsets would I have? Right? So 2 to the power of 15 is 32,768. So what would it be the proper subset? Again, let's go back for a second. What do you notice here between the number of subsets and the number of proper subsets? It's always what? One less, right? Because we're not including the universal set, right? So that means that if 2 to the 15 is 32,768, then that means 1,767, right? It will be just one less. So because the formula for the proper subsets, it will be 2 to the n, and then once you find that, then you're going to subtract 1 from it. Be careful when you're typing this, right? Because it is not subtracting from the exponent, it is subtracting from the evaluation of 2 to the n, right? And then whatever you get, you just take 1 away. So yeah, so this, write it down, take a picture, whatever, because you have a problem just like this on your homework and on your test, okay? So you are going to need to have the formula for the one that I said, use the formula. But the one that I ask you, write the sets, you need to write the subsets, you need to do what I just did here, right? Write every single subset, okay? So just make sure that you do have that one written down. Okay, so, yes, exactly, Guadalupe. So you will have to evaluate 2 to the 15 first and then subtract 1, correct? Yes. And now with a fancy calculator, like this is like if you're doing it on your phone or whatever, but with the fancy calculators, right, when you put power, it opens a little square and then you can put it in, and then you just need to like press like the arrow to the right so you can go outside the box and then be able to type the -1. So I suggest, like when you go and take the test at the testing center, already bring your own calculator. They just need to clear it, and because you already have been using it. Otherwise, go to one of any Dallas College campuses, right, and borrow a calculator from the library, which is the same ones that they will have at the testing center, and get familiarized with it. So in that way, you don't get stressed out that you don't know how to use the calculator. Just FYI, okay? Now, this is the hardest part on this chapter, for this side of the chapter, is operations and sets, which is what you have on page 30, what did I say? Page 28, 29, 30, and 31, right? So you need to know all the different type of operations on the set. So you have unions of set, and unions are like a sum, like you're adding. Like for example, literally addition of whole numbers is defined as the union of two disjoint sets. So yes. Intersection is what do they have in common? That's the intersection. Complement of a set is what is not inside the set. Okay, so I want everything except for this one. So that one is not what you want. So everything else, it will be the complement of that set. Set difference is that you're taking away only specific elements that that second set has that has in common with the other one. And then relative complement, you're going to see that relative complement is written differently, but you're going to generate the same results at the set difference. And then we have the Cartesian products, which again, we only use this when we are trying to write all the different, like we did before, the fundamental counting principle, right? When we're trying to find all the different arrangements. So, right? So again, I know it's confusing because there's a lot of U for union, but also U that right side up U is for universal as well, right? So the universal set, I know there's a lot of U's, but we got the universal set when you talk about Venn diagrams, and then we got the right side up U when we use unions. But if we're doing it with the statement or the verbal one, it will be the word or. Okay, so you can use either the right side up U or the word or. So that's what when you read on page 28, they say number 7, how many students like baseball or tennis, but not swimming? So in that one, you need to put together both the baseball and tennis, because it's a union, and then take away, right? Not tennis, that means the take away, that means the said subtraction. But not swimming, right? So again, that's an additional thing. So the definition of two unions, it contains both elements. So the unions, are you going to bring all the elements of A, you're going to bring all the elements of B, but if they share something in common, you are not going to repeat it, because remember, we don't write repeated terms in a set. So for example, these are two disjoint sets. They don't have anything in common. So that means you are going to include in the union, you are going to include all the elements of A, or, so you're going to use the word or all the elements of B. But you're going to include both of them in the union. Okay? So you're going to say, I want a cupcake from this batch or from this batch. You only want one, you don't want two. Okay? Now, what if, see here you have some numbers. So you have set A, again, disjoint sets, and you're trying to find the union, right? So that means the union of that is going to be the collection of everything. 1, 2, 3, 4 that came from A, and then 5, 6, 7, 8 that came from B. So that is what we call the union for that set. But what if they do have something in common? Then if they do have something in common, you're only going to include it once in the union. So as you see, set C has 1, 2, 3, 4, and set D has 2, 4, 5, 6, right? So when you're writing the union, you're only going to write 1, 3, 2, 4 only once, and then 5, 6. So yes, you still are adding everything on both sets, but whatever repeats, we are only going to write it once. We never write it more than once, okay? And then set intersection, another right side up U, right? A horseshoe, I call it. And then you have the word and, that is the connector, and, okay? And then the definition is, what do they have in common, basically? What do the two terms have in common? Now, if they are sharing, like if they're intersecting sets, that sharing, that is your intersection. So that shaded area is your intersection, whatever is in there, okay? So you want the cake to be tasty and fluffy, not just tasty and not just fluffy, tasty and fluffy. And then we write the mathematical notation at the set of all x's such that x is part of A and X is part of B. So you have to use the connector word and to only refer to this little piece. If you use the connector or, you're going to be shading everything, not just that one little piece. So that's why you see that it's important that you understand the words in the statement format. So as when you're reading the problems in your classwork and your homework, you understand exactly what is there, what symbolic symbols you need to use for set notation. Okay, so again, if the sets are disjoint, right, they do not have anything in common, guess what? The answer is the empty set, right? The null set. There's nothing in common. So it's the null set. If they are intersecting, then whatever is that they have in common, that is the answer, right? C and D in this case have in common 2 and 4. So that will be your answer, just 2 and 4. Okay, and then we have the complement of a set. And that's what I was telling you, that is what is not inside the given set. So the complement of set A refers to all the elements that are not in A, but they're part of the universe. So for example, see, this is A, and that's B, and that's the universe. So when I say complement of A, means everything that is shaded, that is not inside that blue circle. Okay, cannot be inside. Oh, but this part is part of B. I don't care. It's still part of A. So if it's part of A, it cannot be included, even if it's part of B and it's overlapping. Okay, so just be careful for that. And then we can, the different notations, you can write it like with an apostrophe or with a bar on top. And I think I do give you that also on page 25. I give you both of them. I give you complement. And that's what it says. The complement of A is an element of the universe. And remember, not or, and, because it has to satisfy both things. It's a member of the universe and at the same time is not inside A. All right, so that's important that you use the right connector, and, not or. Okay, and then we have, in this case, right, a physical example that you can see it. These are disjoint sets, and I'm trying to find the complement of A, so everything that is in the universe but is not inside A. So what would that be? So that will be everything that I shaded in gray. 5, 6, 7, and 8. Don't forget that it's part of the universe. Okay, so 8 is part of the universe, so it will be there. What if they're overlapping? Once again, you do not want to include anything from the set C. So even though set D has 2 and 4, I cannot include 2 and 4 because that's also part of C. So it will be everything in the outside of set C, which will be 5, 6, and 8. Okay. And I know this is a lot of information. Once again, this is Learning Notes 2.1 on the course resources, because you are going to have to write all this down so you remember which one to use where and when. Okay, now set difference. Again, we don't say subtract it, we say set difference. Okay, yes, we write it as a subtraction, but we say set difference. In some books and online, I have seen it that they use this. A take away B and they use like that slash. For me, that's confusing, but since some of you use Google to search information, I wanted you to see that yes, these two things mean exactly the same thing. Okay, so I just wanted you to recall that. And what does that mean? That means that you have set A and you're going to take away from set A anything that is in set B, that is inside A. Okay, so again, so in the visual representation that this is overlapping, the left crescent moon, right, which is the subtraction of A take away B, you are going to only leave this little piece right here. That little blue part, that is A take away B, see? So because the white part is shared by both of them, but you still need to take it away. So you cannot include that white part right there. So only A, basically. So when you see, remember when we wrote it originally, it says only A, only B, only C? That's what it means. So you're taking away. This is how we write it in set notation. A, take away B. Only A. It's only on A. What about the red one? The red one is only on B and not on A. See, we're taking away again the white part. Okay. So that's how we translate the only parts. That's what we translate. Okay. Now, how do we write it down? We're going to write it down A take away B. It's going to be all the elements of A and right connector and the elements that are not on B, right? So that will give you this part right here. And this one, B take away A, will be all the elements of B and all the elements that are not in A. So you will take away A away from there. Again, take a picture if you want, or just refer to the notes, okay? And just bear with me just a little more. Let me see. I don't even know how many we have left, but so again, here, right? You're taking. They have nothing in common. So if they have nothing in common, there's nothing to take away, right? So that means that if you're taking B from A, right? A take away B, there's nothing. B has nothing inside A. So that means it just will be 1, 2, 3, 4. And then B take away A, again, they're not sharing anything. So it will be 5, 6, 7, 8. So if they don't share anything, there's nothing to take away. Okay, it will be that set by itself. But if they do share something like C and D, right, then you do have things that you will take away, right? So C take away D will be only this half moon, which will be only 1 and 3. And D take away C, it will be only this half moon, which will be 5 and 6. So it does matter if they're intersecting or they're not intersecting. And as you see, this is not commutative, right? Just like any subtraction. A take away a B is not the same thing as B take away A, right? They have total different answers. And C take away D is not the same thing as D take away C. They are not commutative. So it does matter how you write the order or what they're giving you. Okay, so it does matter. Okay, relative complement. Now you're going to see why these two things, the set difference and the relative complement, are so similar. So the complement of A relative to B can also be written down as B take away A. Okay, so or B intersection complement of A. So just to clarify in that part, right? So we already saw the difference. So how does it work with the complement? So what is the complement of A? The complement of A is, hold on, I need to close this one out. The complement of A will be everything that is not. So we're trying to figure it out, this one. The complement of A, right? So it will be everything that is not inside A, right? Everything. So still A will be blank. That's the complement of A. Now, what does the complement of A, this thing that I highlighted over here in blue, what does the complement of A have in common? Because remember, that's what the intersection means. What does the complement of A have in common with B? That little half moon right there, right? This is what they have in common right here, right? This little piece. So, right, let me erase all this. So basically you're left with that right there, the same half moon. So that's why you see that the takeaway, right, the set difference and the relative complement generates exactly the same answer, okay? So that's why you can do interchanging when you're writing the set, but they are named different. So this is called a relative complement when you use the little intersection in the complement. And then the previous one is called set difference because you're actually using like the subtraction sign, right? It's taking away. Okay, so again, I did include some additional practice problems. And for example, in this one, set A includes the letters of the word cats. Set C includes the letter of the words dogs. Set B includes A, C, D, G, O, S, T. So if you find these set differences, right? So if you take B away from A, what happens? B has all the letters of A. So what happens if you take all the letters away from A? What are you left with? Oops, I did it all one point. Okay, whatever. You end with nothing. Okay, I'm sorry, the transition is not working. So you end with nothing, right? But if you're taking A from B, right, then you're only going to take the letter CATS out of here. So you're still left with the letters DOG. So you see that these two things are not the same thing. And the same thing is going to happen with A and C, right? I mean, sorry, C and B, right? So if you take away B from C, you're taking away all four letters. So you're only left with nothing. But if you're taking from B, you're taking C, the four letters away, then you're only left with C, A, and T, right? And then these two, A and C, what do they have in common? The only thing that A take away C, the only thing that they have in common is S, right? So the only thing that they can take away from A is the S, and that's why you're left with CAT. And the same thing here, the only thing that they have in common is S, so they only take away the S from set C, and you're left with DOG. Okay? So it is important that you understand this concept because you are going to be writing these set notations to describe the set that you have in your face, right? So again, and that's what that practice on those pages 28, 29, 30, 31, those are important, okay? And then in general, right, there are properties. So you're going to see there's some properties: commutative property, associative property, distributive property, identity property, complement property, right? And for those, only applies to unions and intersections. See, we have the unions and the intersections are commutative. So A union B is the same thing as B union A. You put them together, right? And A intersection B is B intersection A. Whatever they have in common, they just have in common. We also have associative property, also with unions and also with intersection. Remember, the only thing that changes from the left to the right of the equal sign is the grouping. You can do first A union B and then unite C, or you can do B union C and then unite A. You're still going to get the same shaded area or the same numbers, sets, members, whatever, right? And the same thing happens with the intersection. And distributive property is a combination of both. A intersection over the union, and then you're going to do A intersection B, A intersection C, and then you're going to unite those two with this operation in the middle. But if you have a union in the outside and an intersection in the inside, then you can do A union B, A union C, and then connect it with the intersection. Okay? And then we have identity property. So it varies, right? So the identity property in a union, remember, union is like addition. And remember, what is the identity in an addition? Zero, right? If you add a number to zero, the number doesn't change. So in this case, it's the empty set. So if you add the empty set to a union, right? The union and the empty set is still that set, A. And then in an intersection, right, you find out what they have in common. So obviously, if what the universal set, which is everything, what do they have in common with the set A? It will be just set A. And then you have the complement property, right? So think of the complement property as the inverses, right? So well, in this case, if you have A and you're adding everything that is not inside A, which is the complement of A, then you get the universe, right? So if you have A and then you add everything that is not in A, you're going to get the universe. Now, if you have A and you want to find what they have in common with the complement of A, that will be nothing because they don't have anything in common. Okay? They don't. So, additional properties of sets, right? The law of the universe union with any given set is going to be the universe because the universe has more elements than just A. Law of the empty set, if you have the intersection with an empty set, it's like a multiplication by zero, right? So intersection is like a multiplication by zero in this case if you have the empty set. So if you're intersecting with nothing, it's going to be nothing. They don't have anything in common, right? And then you have the De Morgan's law, and you're going to see that there are different varieties. So how I use this on your homework and on your test. So the way that I use this, I don't ask you, what is the De Morgan's law? No. Since you need to translate, right? You need to translate given Venn diagram into set notation. You have the option of writing it this way or writing it that way. So basically, you're using the De Morgan's law. You will have it correct if that's what you need to do, right? You will have it correct if you write it this way, like the complement of the union is the same thing as the intersection of the complement of each individual set. Or the complement of the intersection is the union of the complement of each individual set. Okay? So if you write it that way, that will be okay. In the double complementation, of course, right? The inverse of the inverse is the original. So again, the complement of the inverse, what is the complement of the complement? The complement of the complement is the original, right? Which is A. In the law of the empty set and universal set, right? The complement of the empty set, it will be the universal set, and the complement of the universal set, it will be the empty set. Okay, so again, I am not going to ask you this to define any of this. You just need to know how to use it, okay, when you're defining sets. I hope that makes sense. And then here, this is very similar to what you have on, like on the bottom of page 29, like from 7 to 14. And then I don't know if you have looked at page 30 and 31. So on page 30, I give you the shaded set, and I was good in this case in the workbook. I gave you a multiple choice on the bottom, and there's one correct multiple choice per set. Because otherwise, if you guys come up with your own, you can come up with different ways of answering the same question, right? So I just thought that maybe, it will be easier for you. So again, I give you you have something very similar to this on your, I think in your homework, and on your test, right? So I give you the set, and you need to be able to tell me what is the intersection, what is the set difference. And this, let me show you the difference between this and this. In this one, you first need to find on number C, letter C. You first need to find the union of A and B. And once you have found the union of A and B, then you're going to find the complement of that. So in other words, everything that is in the universe that is not inside A union B. Okay? So for that one, let me see if I can write quickly. Oh, no, eraser. Okay. So for that one, for C, you're going to have to first find A union B. And then that one, and bear with me because I'm writing with the mouse. So that will include 1, 2, 3, 5, 6, 8, 10, plus 2, 4, 6, 8. And we're not going to write it twice. So we're going to write 1, 1, 1, 2, 1, 3, 1, 4, because 4 is over here. 1, 4. 1, 5, because we have 5 on A. 1, 6, even though they repeat, I'm only going to write it once. We don't have 7, but we do have 8 on both of them. So I'm only going to write it once. And then A had 10. This is your first step. Find the union of A and B. Now that you have all the numbers listed of the union of A and B, now we're going to find the complement. What is in the universe, but it's not an A and B? So what is in the universe that is not an A and B? So the universe has 1, right? The universe has 2, the universe has 3, the universe has 4, the universe has 5, the universe has 6, 7. 7 is not in this union. We got 8, 9 is not in this union. We got 10 and 11 and 12 is not in this union. So what will be the complement of the union? It will be 7, 9, 11, and 12, right? Because that is part of the universe, but it is not part of the union. So when you're doing this type of problems, it is essential that you do it little by little, okay? So, and like order of operations, right? D, you will have to find first what is the intersection of A and B before you can take it away from C, okay? So what do A and B have in common? So A and B have in common 2, and have in common 6, and have in common 8. And then, so now that you know that it's 2, 6, and 8, then you're going to take that away from C. So the C has 2. No, so I cannot take it away. The C has 6. No, so I cannot take it away. The C has 8. Yes. So that's the only number I'm taking away from C. So what are you left with? You're going to left with 1, 3, and 9. Does that make sense? Which is not the same thing you have to do in E. In E, you have 3 operations. So you first need to find the union of A and B. Then you need to find the complement of C. And then once you have those 2, then you're going to take away the union of A and B from the complement of C. So you see, this one is a little longer, right? So because you have to do more steps. It's like order of operation, right? And I think let me see, did I fix it? Yeah. I don't know why these are not fixed, but anyways, so yeah, so see right here, so it's whatever is left. So these are just the answers, but again, you want to be able to go practice, right? So write them down, practice, and then you can check the answers on the next slide. And then I think you have one like this as well on your homework. And you have one very similar to this on the test as well. So I'm giving you a Venn diagram, or I'm not giving you a Venn diagram, I lie. I'm just giving you this information. And you have to draw the Venn diagram, and you need to fill in the Venn diagram with the right thing. Now, this is where students messed up. Remember that when you have 2 or more intersecting Venn diagrams or sets, you need to start with what they have in common first. So the first thing you have to need to find is what goes right here. What do they all 3 have in common? That's the first thing you need to find. And that is the people that have the desktop, a smartphone, and a tablet. And they say there's 18 people that have a desktop, a smartphone, and a tablet, okay? So 18 needs to go right there, okay? So let me do clear. So you're gonna write 18 right here. Now, you need to, it's supposed to be an 18. So you need to account that at that 18 is already included on the desktop people, is already included on the smartphone, people, and is already included on the tablet. So when you are looking into, let's see if I can move this. When you're looking into these that said 43 people have a computer and a smartphone, so 43 people have a computer and a smartphone, these two need to add up to 43. Including, that 43 includes the 18 already. So you need to do 43 minus 18, right? And that's going to give you the number that goes up here. And then those two, along with whatever this number is, this will be the people that have a desktop and a tablet. So desktop and tablet is 25, but you already have 18. So you will have to do 25 minus 18 to find this number over here. And then when you're trying to find the total number of people with a desktop, you're ready to add this number plus this number plus this number, and then subtract it from the total number of people that have a desktop, which in this case is what, 76. So 76 does not go here. You got to subtract all these three numbers from 76. So when you do that, again, I think I did do it on the next page because I said answers on the next page, right? See? So 25 have only a desktop and smartphone. Only. See how the word only? But 25 and 18 have both desktop and smartphone, but 18 also have a tablet, right? So 7 only had a desktop and a tablet, but 7 plus 18 had both a desktop and a tablet, and 18 of them have a smartphone as well. And then if you add 26 plus 25 plus 18 plus 7, you are going to get the 76. So that's why you want to fill the smartphone. You want to fill the Venn diagram first, and then make sure that you can answer the questions. Now, you're going to see that I have a 9 here. Where does that 9 come from? Well, once you fill the 3 sets, you're going to add all the numbers once, and you're going to subtract it from the total number in the universe. The total number in the universe is 120. So since this was less than 120, I think there was a difference of 9, so that means that will be 9. This will be the number of people that do not own any of these 3 devices, right? So, and you also need to know how, you also need to know how to write the set notation. You see what I'm saying? Because you're going to have to write the word. So instead of me asking you a question, I will give you this. I will give you D intersection S, take away T. I'm not going to give you the number. You need to find the number. But I'm going to tell you, what does this represent in words according to this? And you're going to say, these are the number of people that own a desktop and a smartphone, but not a tablet. So you need to write in words on the homework and on the test this. So I'm not going to have a question. You're going to have to write it down. Okay? So not only you need to write down the set notation, but you also need to write down the word part of it. Okay? So, and that's why it throws students off a little bit. So I am going to end it here because we are like way over time, right? But I'm going to end it here. And what I want you to do for next Wednesday, since again, the homework is not due next Wednesday, is do the after that. What I'm going to do is that if you have worked on these problems online, on the workbook, sorry, and you have questions about this on the workbook or on the homework, right? I can go over those, okay, next class. And then I will try to finish the other part of chapter 2, which is again 2.2 learning notes, which is all about conversion, different numeration system and conversion to different bases, okay? And that's another chunk of information that you're going to have to work with. So again, chapter 2 is loaded. as chapter 3. So 1, 2, and 3 are the loaded chapters. After that, it's much easier. So it will go much faster. But yeah, but I will go over the next part next class. Okay. And I appreciate your patience today. I did not plan to have all these internet problems and, connections problems. And I also appreciate that you stayed that little extra time to be able to finish this first class notes. Okay. And I will upload it. It's supposed to be in the cloud. So once Zoom tells me that it's ready in the cloud, I will upload it to my Google Drive. And then once my Google Drive is done, then I will upload it to, you should be able to have access in the links. Okay. For this section, do we have to work as an elementary? Yes. So some of these things, every time that you have to, like there's a word problem and you want to be able to do, yes, you want to be able to do it as a elementary students. But some of these specific things, like how to work with set notations, no. This is just you understanding, okay? So no, I hope that makes sense. If not, just let me know. Okay. But again, I can address questions for the homework specifically next class, because that should be like half of your problems, 5 questions of your problems on the homework. And then the other 5 questions will be from the second part of chapter 2. Okay, thank you. And have a good evening, everyone. Thank you. Thank you.